finally, I'd like to introduce our speaker for the night. We're pleased to have Robert Farrauto from Engelhard. Dr. Farrauto is a principal scientist in the R&D department of Engelhard Corporation, Edison, New Jersey. He has conducted research and product development in all phases of catalysis for the environmental, chemical, and petroleum industries. He is currently managing a research team dedicated to commercializing new after-treatment technology for the catalytic abatement of emissions from diesel engines. He is the author of 35 publications and 15 U.S. patents, mostly in the field of heterogeneous catalysis. He is also adjunct professor of chemical engineering at Stevens Institute of Technology and the New Jersey Institute of Technology, where he teaches a graduate course in industrial catalysis. He has a BS in chemistry from Manhattan College in New York City and a PhD in chemistry from Rensselaer Polytechnic in Troy, New York. Bob.
Thank you very much, Bernie. And I want to thank Bert and John Stencil for inviting me here. It's very, very nice to be here, and I appreciate all of you coming because I had to change the schedule due to some travel arrangements I had. So the reason there was a date change was because you were trying to accommodate me, so I appreciate that. The last time I was in Lexington was in May for the very successful North American Catalysis Society meeting. And at that time, it was announced that the 90s would be the decade of the environment. And that's good because that's one of the things that we in catalysis do quite a bit of. That is environmental science, pollution abatement, etc. However, the environmental movement really started. The environmental movement really started back in the late 60s, early 70s when the Clean Air Act was passed. And the technology that was derived from the Clean Air Act was primarily related to the automotive catalytic converter. And since that time, a lot of technologies have been derived from that. And consequently, you can think of the automobile catalytic converter as the parent, and all of the descendants are things like stationary pollution abatement and other types of pollution abatement related to mobile sources. And now, as was announced, we're very actively looking at the control of emissions from diesel engines. So what I'd like to do tonight is give you an overview of some of the existing technologies that are currently in practice for environmental control involving catalysts. And as I mentioned, the auto exhaust is certainly the most predominant. We'll have something we'll talk a little bit about the basic technology. Basically, it involves precious metal catalysts, and they're pretty much supported on honeycombs, these monolithic structures, which I'll show you some pictures of soon. One of the descendants of the automobile catalytic converter is the so-called stationary abatement. And here we're talking about catalytic devices that are used for controlling emissions from a variety of stationary sources. These are chemical plants, where they might be painting a particular car body, for example, in an automotive application, or they may be coating wire, or maybe in a power plant where you have CO and hydrocarbon emissions, or, which is now becoming very critical, is the NOx emissions. So NOx, NOx, is the one of the major pollutants that emanate from power plants, and therefore there's a lot of technology that's directed towards trying to make the catalyst abatement much more cost effective. And the platinum-based catalysts were used for the stationary organic oxidations, whereas for the reduction of the nitric oxides, effectively it's vanadium titanium, although some new catalysts are being introduced now. They're zeolite catalysts for higher temperature application. And then finally, there's another interesting one that we'll talk about briefly, is ozone abatement in airplanes, and this is related to the air that enters high-flying aircraft and how it needs to be purified. So these are some of the existing technologies, and then we'll get into talking about some of the things that are on the horizon, some new types of technology, all of which involve catalysis, all of which still have problems that need to be solved. Let's talk briefly about the automobile catalytic converter. The normal combustion reactions that occur in the internal combustion engine are things like the combustion of benzene or branched hydrocarbons, and the complete combustion of these organic materials lead to, in addition to CO and water, obviously you produce energy, and that energy is the useful part that is used in the power stroke for the internal combustion engine. These reactions, as they're written here, are shown to be complete. But in reality, due to mixing, due to lack of efficiency, etc., there are situations where the combustion process is less than efficient, and it results in significant quantities of things like carbon monoxide. Anywhere from 1 to 2% of the emission is carbon monoxide. Also, because of cracking reactions and other things that occur, you can get hydrocarbon concentrations up to about 0.1%, or about 1,000 ppm. And these are typically the hydrocarbons that are involved. On the other hand, due to the high temperatures in the internal combustion engine, you get nitrogen fixation reactions where the nitrogen and the oxygen react homogeneously and produce NOx. And NOx is the symbol that's usually used for NO, NO2, N2O. And generally it's anywhere from about 100 to 300 parts per million of NOx in the emissions. The history is very interesting as to what technologies were ultimately used, and I don't have time to get into why General Motors went one way and Ford and Chrysler went another way, but basically most of the world right now is moving towards these monolithic honeycomb structures that are effectively ceramic in nature, although there are some metal substrates that are now becoming of interest. But these materials have a variety of cells, and usually 400 cells per square inch is typically what is used in the current automobile catalysts. And the ceramic material is simply used as a support or as a structure upon which the catalyst coating is deposited. So the catalyst is deposited on the walls of the channel, the pollutants emanate from the internal combustion engine, pass through the honeycomb, interact with the catalysts, and the catalysis reactions occur. And the honeycomb or monolithic structure is particularly popular because it has very low pressure drop. It has about a 70% open frontal area, which means you have very low back pressure, which translates to a low fuel penalty. And also because you can pack a lot of cells per square inch into this device, you can have a very high surface area device with relatively small volume, and thus from a real estate point of view it fits in nicely underneath the automobile. Now that, if we take any one channel of that, oh by the way, let me show you where the catalytic converter fits into the automobile in case you don't know already. It's, at least in this particular shot, we have it before the muffler, but the catalytic converter is right underneath, usually the passenger seat. And the gases, these are connected to the engine manifold, the gases pass through. Whoops. This is a single channel of a honeycomb, and the catalyst coating is deposited onto the walls of this monolithic material, and I'll have a little more to say about that in a few minutes. The catalyst is deposited on the wall, and the pollutants, fuel or air, etc., is passed through this channel, of which there are at least 400 per square inch, as I indicated earlier. These pollutants diffuse through this stagnant layer into the catalyst coating, get combusted to CO2 and water, and then you exit the actual tailpipe. The monolithic converter is mounted or packaged, if you may, in the exhaust manifold. And as you can see, you have to have the right, here's the honeycomb catalyst, you have to have the right angles in order to present uniformly to the face of the honeycomb the pollutants and the air mixture. The material here is used for both insulation as well as for shock, because the material very often will bounce over highways and roads, and to keep it from fracturing you have to have the proper type of insulation. If it's not canned properly, these things can break very easily. And as I'll mention later on, the newest automobile catalyst converters have another device that's right here in the inlet to the honeycomb, which is called an oxygen sensor, and that's used to control the air-to-fuel ratio. Okay, let's talk about the catalysis a little bit. In 1976, which was when the first catalytic converters were actually installed in the United States, the only pollutants that needed to be treated, that couldn't be treated through engine modification, were the CO and the hydrocarbons. And the CO is an oxidation reaction to CO2, and the hydrocarbons to CO2 and water. And the catalyst that was used for that is roughly 2.5 platinum to 1 palladium, and it's usually on some type of a stabilized alumina material. Now that was fine until about 1980, because up until this point the NOx standards were not that critical that they could not be met by engine modification. EGR, exhaust gas recirculation, was the common method that was used. But in 1980, the so-called three-way catalysis became popular, and there you have to oxidize CO and hydrocarbons just like you do here, but yet you have to reduce the NOx. So you've got the problem of you need an oxidizing environment for 2 of the pollutants, you need a reducing environment for the third, the NOx, to make nitrogen. And I'll explain how the oxygen sensor fits into providing the proper air-to-fuel ratio that is sufficient to get all 3 of these. But basically, the catalyst that is now currently used in almost all automobiles sold in the US, as well as in Japan and soon in Europe, is a 5-to-1 ratio of platinum to rhodium on aluminum. The alumina usually contains other things, stabilizers, so-called oxygen storage components, things like cerium oxide, nickel oxide. So the technology is much more complicated than one would imagine from looking at it here. But basically the reactions, you can see, the CO and the hydrocarbons and hydrogen are oxidized, the NOx is reduced, and the NOx is reduced sometimes by the CO and the hydrocarbon. Taking a closer look at that catalyst deposited on the ceramic material, this is a ceramic material. It's called cordierite. It's a magnesium aluminosilicate material. It's got very high temperature stability characteristics. It also has very low thermal expansion, so consequently it is very resistant to thermal shock, which causes cracking. The catalyst coating, which is effectively alumina, and in the case of oxidation, it's platinum palladium, and the three-way catalyst is platinum and rhodium. The catalytic metals are deposited on the alumina or within the alumina wash coat. That's what we call this. And as you can see, it is deposited on the ceramic material. It is bonded basically physically as well as chemically. There are pores, and you can see some what appear to be holes in the ceramic wall, and they serve as mounting points for the physical bonding of the wash coat to that ceramic material. And obviously you're talking about relatively high linear velocities in the auto exhaust, so you have to have good adherent coatings to that ceramic. Okay, I mentioned that the current technology, the three-way catalysis, takes advantage of a very important development that occurred in the late 70s, the so-called oxygen sensor. And the oxygen sensor allows you to do all 3 catalytic reactions, the oxidations as well as the reductions, and it works as follows. If this is conversion, and this is the air-to-fuel ratio, which the carburetor is functioning, you can see that when you are very rich of stoichiometric, indicating that you have more fuel than air, you're rich in the sense that you don't have enough oxygen to combust all of the fuel. In that case, the abatement of CO and hydrocarbon is going to be relatively low. As you move towards the stoichiometric point, where you have a lot more oxygen present, then you can begin to oxidize the CO and the hydrocarbons, and you can see that there's a point where you get very high conversion of CO and hydrocarbon, particularly as you go further in the lean regime where you have an excess of air. On the other hand, the NOx, which requires a reducing environment, its conversion is very high at the rich condition, because obviously you have extra fuel that can reduce the NOx, and that conversion stays high until you get to this air-to-fuel ratio where you start going lean, and then the NOx conversion drops. So effectively there is a window, very narrow window, air-to-fuel ratio, where you can get effectively 80 to 90% conversion of the 3 pollutants simultaneously. And that's why the term three-way catalysis is used for these. And the oxygen sensor is the device, as I mentioned before, that is at the inlet to the catalyst face. It senses the oxygen, it feeds back to the carburetor, and continuously adjusts the air-to-fuel ratio so that it's constantly perturbed between these 2 regimes so that you get all 3 conversions to occur simultaneously. So that's effectively what the existing technology is in the automobile. I'll just briefly mention the fact that these catalysts do deactivate. They are federally required to go 50,000 miles, and that's soon going to change to 100,000 miles. But basically, if you think of this as a model for a catalyst carrier, for example, this is alumina, and these spots here represent platinum, palladium, or rhodium atoms, or clusters, or crystallites. The reactants must interact with these metals in order to undergo catalysis. Now, you've got a pore in which, and most of the catalyst wash coat material is very porous, so consequently, these reactants have to be transported into the porous network in order to interact with the catalytic sites and get converted. So that's fine until you start going to very high thermal stresses on the catalyst. And these thermal stresses can have a major impact on the structure of this carrier material. And this carrier material can undergo sintering, and you probably are all familiar with that from your own work in petroleum or chemical areas. And this sintering phenomenon is much more pronounced in the auto exhaust, mainly because the temperatures are quite high. In the automobile, you can get temperatures close to 1,000 degrees centigrade, depending on how the car is being driven. So consequently, getting aluminum materials to be stable to temperatures as high as 1,000 degrees, at least for periodic increases in temperature to that point, was a major challenge. And if you don't do that, what happens is you get this sintering, which is effectively a bottlenecking, and you choke out these active sites, and hence the reactants can't arrive at those sites. And that is generally stimulated by thermal, but certain environmental impurities can also have an effect. Things like sodium and chlorine, etc., can have an impact on the sintering rates. Similarly, the metal can undergo a different type of mechanism, but it's agglomeration or Oswald ripening, if you may, where these small crystallites have a very high surface to volume free energy. Consequently, there is a propensity for them to grow into large crystallites, and when that happens, the crystallites only on the surface are available to the reactants. The crystallites of platinum or rhodium that are underneath are no longer available, and consequently you've gone through this metal sintering phenomena, and that metal sintering results in a decrease in the overall activity. So basically the catalysts had to be developed to be able to resist periodic increases in temperature up to about 1,000 degrees. And this is still a major problem that exists, but obviously the enhanced control in automobiles is minimizing the thermal stresses on the catalyst. But one that doesn't seem to want to go away is the selective poisoning. And just as in the chemical and petroleum industry, there are poisons that influence the automobile catalyst, the most notable of which was lead, which was in 1975, 1976, was removed in general from the gasolines, although there's anywhere from about 3 to 5 milligrams per gallon of lead in unleaded gasoline. So that lead represents a potential poison where it selectively reacts just with the catalytic metals, in this case the platinum or the palladium or the rhodium. It alloys, it deactivates the catalyst by forming some new type of a compound. So that's the reason why lead came out of the gasoline initially, and lead is going to be further reduced in unleaded gasoline to levels below 1 milligram, so that'll increase the overall life of the catalyst. But other things, I mean mercury, arsenic, etc., gaseous poisons, SO2, sulfur is present in gasoline. It is a product of the combustion reaction, as is SO3. And both of these, SO2 and SO3, can absorb onto the metal sites. Usually, if it absorbs onto the metal, it's more of a reversible poison, where if you get a high temperature spike, SO2 or SO3 will desorb from the surface, unless you get SO3 that reacts with the alumina, in which case you form aluminum sulfate. And sodium chloride generally is a problem, particularly near oceans, where the air may contain various amounts of sodium chloride. H2S has become a problem now as a result of the three-way catalyst, where you are under certain conditions in a reducing environment. And in that case, SO2 that's absorbed on the catalyst can get converted to H2S. And some of you may have smelled that in your automobiles. And there's a lot of interest right now in trying to learn how to control the H2S emissions from the automobile catalytic converter. Just as in the petroleum industry, where you've got coke formation, you can get fouling on catalyst, which is effectively debris that deposits indiscriminately onto the catalyst or within the catalyst pores And usually phosphorus resulting from the lubricating oils is one of the major sources of that. And that phosphorus tends to deposit on the catalyst, but primarily it kind of builds up in the arteries, if you may, of the catalyst, and tends to enhance pore diffusion resistance, and as a result, you've got a greater resistance to pore diffusion, and that ends up decreasing the overall rate of reaction. And again, the possible use of non-phosphorus oils is something that's on the horizon. You've got to get this coating to stay adherent to the monolithic substrate. And again, here's our model of our alumina coating with the precious metal on it. And it is bound both chemically and physically to a ceramic oxide. So you've got strong chemical bonding. The materials had to be developed to be compatible with regard to thermal expansion, because the car catalyst will see various differences in temperature, and as a result, if there's too big a difference in the thermal expansion, as indicated by this line, you can get a ripping or an attrition, what we call exfoliation, of the wash coat from the ceramic. That's a very serious problem with metal substrates, because obviously metals have a very high thermal expansion relative to a ceramic, and therefore the technology to bond the coating, the oxide, to the metal has to be very, very unique in order to get good adherent coatings. Okay, that's basically what I wanted to say about the auto exhaust. And as I mentioned earlier, the automobile catalytic converter was really the parent of many technologies. And one of the technologies that developed from that was the idea of stationary pollution abatement, particularly of organic materials. Some of these are shown. This is a plot of just conversion versus temperature. And you can see the different ranges on which these different kinds of materials undergo catalytic oxidation. And the catalytic processes are now generally favorable compared to incineration, because here you can operate at lower temperatures due to the nature of the catalyst. You don't have to have expensive materials of construction. Your fuel costs are much lower because you don't have to add additional fuel as you would in a thermal incinerator. And naturally, you don't produce the high temperatures that you would in an incinerator that ultimately result in NOx. So stationary abatement in chemical plants, in painting operations, even in bakeries is becoming a very much a approach of choice. And just give you some idea of what the design basically looks like. You have the pollutant gases coming in, you have some kind of a distributor. You need some burner to get your preheat temperature up high enough. Those gases then are properly mixed and thoroughly passed through the honeycomb, hopefully uniformly, and they're combusted, and they go to the effluent. If you've got a high concentration of pollutants where you get good exotherms, high exotherms, you can also use that heat exchange to preheat the gas and then put less demand on the burner. And then if you further continue, you can have a secondary heat exchanger to even heat process air. Again, it depends on the nature of how dirty the feedstock is. Okay, a technology also in the stationary abatement applications that is getting a lot of play, particularly here in the United States now, is called SCR, Selective Catalytic Reduction. And here we are trying to selectively reduce nitric oxides, NO, that emanate from the power plant. Power plants obviously are burning fuels at temperatures well in excess of 2,000 degrees. In other words, points within the flame or in the combustion bring you over 2,000 degrees, and consequently you can get fairly high concentrations of NO, maybe 150 to 300 parts per million. And that NO has regulations now, it has to be removed. And the technology that appears to be getting the most play right now is the so-called SCR, where you inject ammonia through a manifold system. It passes through this catalyst, which turns out is vanadium on titanium. That's the primary catalyst that's used now. That reaction is very selective in that the ammonia, instead of reacting with the oxygen to make NO, actually selectively reduces the NO here. So instead of having the undesirable reaction, which actually makes NO, this catalyst is selective enough that you can reduce it all the way down to nitrogen. Okay. We're going to say a little bit more about this a little bit later on. One of the very interesting applications for catalysis that very few people know about is related to ozone abatement. We hear a lot about atmospheric ozone and ozone in the ionosphere and the troposphere. it turns out that if you make a plot of altitude versus the ozone concentration, you can see that the ozone starts building up, and it depends on location, etc. The ozone concentrations are usually highest in the polar regions, the North and South Pole, although I guess it's getting depleted. But in any event, there are significant concentrations of ozone. Now, when airplanes, commercial airlines, are flying to Europe or flying to Asia, they fly over the polar regions, and they are flying typically between 40 and 60,000 feet. And consequently, when they're bringing in air from the outside, that air has got some ozone in it. And that ozone will make the passengers and crew airsick. So consequently, there is technology that's been developed to catalytically abate the ozone before it actually enters the airplane. And that technology is present in all of the 747s, mostly all the wide-body airplanes, and some of the newer ones, even the 777, the new plane that Boeing is developing. But basically, the advantage that the catalyst has is to take the ozone and simply decompose it to oxygen. And this has to be done at a relatively low temperature because you want to be able to take the discharge temperature from the compressor. Because when you're bringing the air in from outside, you've got to compress it. It's very cold, and it's so consequently, to compress that, you bring it up to about, this is in degrees Fahrenheit, you bring it up to anywhere from about 250 to 300 degrees Fahrenheit. That's typical compressor discharge temperature on a major wide-body airline. And as you can see, catalysts actually do function in that temperature, the right catalyst does function, whereas a thermal process would require much higher temperatures in order to get the kind of required reductions. So this is a very neat application for the use of catalysts in the commercial airlines. Okay, in the introduction we mentioned about diesel. This is a schematic of what the exhaust of a diesel engine might, a cartoon at least of what it might look like. And anybody that's driven behind a bus or a truck knows you don't see quite this. What you see are these things. Okay, well these things are the dry soot particles that we often see. In addition to the dry soot particles, you also have, as indicated by this key, you have free liquids that are represented by these open circles. And these liquids are usually lubricating oils that have not been burned. And these lubricating oils add to the particulate load, if you may, of the emission from the diesel engine. So these things may be gases when they first come out of the engine, but then as they're cooling, as they go down the manifold, they start to condense. So in addition to these liquids and these solids, you also have gases that are indicated by the dots here, and these gases are things like CO and hydrocarbons and sulfur dioxide, because again, sulfur is present in diesel fuel. And also, this thing represents a sulfuric acid particle. You've got anywhere from about 2,000 to 3,000 parts per million currently in diesel fuel. And as a result of the combustion process, some of that SO2 gets converted to SO3. And as that SO3 is being cooled, obviously what happens is it becomes somewhat of an aerosol, and you've got sulfuric acid particles coming out. So consequently, the emission from the diesel engine is a three-phase exhaust. And how is a catalyst going to be able to function in this kind of environment? If you think about the automobile catalyst, which we thought was a tough job, there you're only dealing with gases. Here you're dealing with all of these different types of structures. And in 1994, there will be in place federal regulations that require that the particulate emissions from diesel engines be reduced below a certain value. And the primary source at which the catalyst can function is to primarily eliminate the liquids and some of the gases and not produce any sulfate. Because, if you think about it, a catalyst that oxidizes CO and hydrocarbon, or that oxidizes these liquids, is probably going to oxidize SO2 to SO3. I mean, if you recall, platinum catalyst used to be the catalyst used for the production of sulfuric acid. And they do seem to be the metals of choice for the diesel emission. So the trick here is to be able to combust the oxidized CO, hydrocarbons, and liquids, but without oxidizing SO2 to make SO3. Because if you make SO3 in the catalyst, then you're making these things and they add to the particulate load. So there's a real problem in developing selective catalysts that simply oxidize the organics and not the SO2. And there are technologies that will be installed in 1994 to deal with this. Now these soot particles are being eliminated, or I shouldn't say eliminated, but they're certainly being minimized by the engine manufacturers. There are many things they can do to modify the amount of dry soot that comes out of the engine. And what they're basically doing is sacrificing. They're making less of this and they're making more liquid. And the reason they can do that now is because the liquids and the gases can be handled through a catalytic system, whereas the solids would have to be handled through some type of a filter. So it's easier to simply treat the gases and the liquids as shown in this cartoon. Again, here we have a honeycomb. They have the catalyst deposited on the walls. It's very similar to what you see in an automobile catalyst, except these honeycombs are much larger in diameter. You've got CO, you've got hydrocarbon gases, and you've got liquids. They pass through this honeycomb catalyzed system. They are converted to CO2 and water, and hopefully you're not making any SO3 out of any of the input SO2. And that's the problem in selectivity. And as I mentioned, in the automobile catalytic converter, catalyst has to function for 50,000 miles. In the diesel, it has to function for 290,000 miles. So it's a much more demanding application, and therefore the catalysis is much more complicated. But yet there is technology that will be installed, and right now people are writing contracts with companies to install catalysts in these devices. Now, one of the other issues that is going to be more difficult to handle from diesel engines is that of the NOx. And the NOx is a problem because diesel engines do make quite a bit of NOx. The problem is you are very oxidizing. A diesel engine operates very, very lean. And therefore you don't have the benefits of the three-way automobile catalyst technology where you can simultaneously do all three by controlling the air-to-fuel ratio. So people are scurrying around trying to find ways in which you can decompose NOx. Now, we talked about SCR, selective catalytic reduction, where you inject ammonia. And certainly that technology can work here, but nobody wants to carry a tank of ammonia around with them. Okay? So consequently, we're looking for ways in which we can reduce the NOx using the exhaust gases. And this is very, very difficult, and it turns out right now that the only materials that look partially feasible are some zeolite materials, some small pore ZSM5 type zeolites with copper on them. And these zeolites, in some way, nobody quite understands the mechanism, that what it's believed happens is that the small pore excludes the oxygen, and the CO and the hydrocarbons enter into the pore structure along with the NO, and you have a net reducing environment in that localized environment, and then the reduction occurs. But those catalysts still only function within a very narrow temperature range, like between 400 and 500. They are, because they contain copper, they can be influenced by sulfur. So it's a real challenge, and this is one of the technologies that will have to be developed in the future, and right now there really is no potential solution for it. The final topic I want to mention here is a very exciting type of combustion. And it differs from all the other pollution abatement technologies we've talked about, because all of those treatments we talked about earlier were after treatments. You generate the pollution and then you go clean it up. Well, here is a technology that's called catastrophic combustion, and it effectively eliminates the pollution at the source. You use a catalyst to combust the fuels, and you don't produce any CO, hydrocarbons, or NOx. Okay? Sounds great. And if you look at how it functions, here is a conventional combustor that might be used in a power plant. And here you bring in fuel to air, and you've got to be fairly close to stoichiometric in order to bring these in so that you reach a condition where you generate a flame. So you have to have a flammable mixture to start with. And in generating this flame, the temperatures are very high. As I said, some of them can go up to 2,000 degrees in certain portions of the flame. But that temperature is too high for the blades of the gas turbine. So consequently, you then have to add dilution air in order to cool that high temperature gas in order to make it compatible with the temperature requirements of the turbine blades. So if you go through this whole step and you plot it of temperature against profile down the combustor, you can see what happens. You combust your fuel, you generate temperatures around 4,000 degrees Fahrenheit. So you are well in the NOx formation range, and NOx generally forms around 2,700 degrees Fahrenheit. That's when the rates are fairly high, which is about 1,600, 1,500 degrees centigrade. So you form the NOx, and then you have to cool the gas by dilution air in order to make it compatible with the blades of the turbine. Instead of burning the fuel thermally, you can use a catalyst. You can start with a leaner fuel-to-air mixture, because a catalyst doesn't require that you have a flammable mixture, because you're oxidizing. You're not combusting in the same sense as generating a flame. That's why catalysts often are talked about as being flameless combustors. Anyway, you inject a leaner fuel-to-air mixture into the face of a honeycomb catalyst. You need honeycombs because the pressure drop constraints of a power plant. The gases, again, pass through the honeycomb just like in the other applications, but you generate a very high temperature and you then present that gas to the gas turbine blades. Now, the distinction is you are starting at a leaner fuel-to-air mixture. You initiate catalytic reaction, and you see this little plateau here, which corresponds to traditional mass transfer control. By unique design of the catalyst, the process, the temperatures, as well as the gas composition, you can get an extra amount of combustion that is related to thermal reaction. In other words, you've got a catalyst that initiates a catalytic reaction, and then superimposed on that, you get a thermal combustion. It's not a flame, it's a thermal reaction that occurs, which then completes the combustion, yet your temperatures are low enough that you do not go into that NOx formation regime,